In this kinematic problem, we have an airplane sitting on the runway. It's at rest. On this day, there is no wind in any direction, 0 miles per hour for the wind. And this plane is going to accelerate uniformly for 38 seconds from being at rest to the time it takes off. And that, for this particular model of airplane, requires 150 miles per hour of airspeed, which will equal the ground speed because there's no movement of the wind. So let's go ahead and continue this problem. How would we approach this? Well, we have uniform acceleration presented to us in this problem, so we can make use of the kinematic equations. We'll get to those. But first, let's make a little sketch of what's happening here. A simple airplane at rest, V0 equals 0. At the takeoff point, its ground speed and its airspeed will be 150 miles per hour, and that's 38 seconds after the time it starts accelerating. So I want to use metric units for this, of course, so we switch from miles per hour to meters per second with this conversion factor. Multiply by 0.447 meters per second, divide by 1 mile per hour. And now we move to the kinematic equations. The direct method here is to use the first kinematic equation. The final velocity, the takeoff velocity at time t, 38 seconds in this case, is found by taking our starting velocity at time equals 0 plus acceleration multiplied by time. Inserting the numbers, 67.1 meters per second for our takeoff velocity at the time of 38 seconds. The plane starts from rest, so 0 meters per second for V0. And you can see we have to divide both sides by 38 seconds, and that will produce an acceleration 1.77 meters per second squared. You should check this on your own calculator. All right. Coming back to part B, what is the minimum length of runway that's going to be required for this takeoff? What's the minimum length of the runway? We know the acceleration, we know the time, we know the final velocity, we know the initial velocity. So there are actually a couple of choices we could use. We could use what I call the third kinematic equation, that x equals x0 plus v0 t plus 1/2 at squared. X is the position along the x-axis, and v0 we've already encountered. I'm going to use the first of these equations, and you probably should go ahead and use the second equation and double check my work. So this equation simplifies because we're going to say that the position at time equals 0 is 0 meters, so I put a 0 in for x0. V0 is a 0, so that multiplied by the 38 seconds produces 0. 1/2, we know the acceleration, we know the time, and don't forget to square in this equation to find x. Again, you should pause, do this on your own calculator. I came up with 1,278 meters, and converting that to miles with the conversion factor that 1 mile is 1,609 meters, I came up with about 0.8 of a mile, 0.794 miles. So the key here is that we do have uniform acceleration, constant acceleration. That's an approximation for this situation, but not terribly far off. You can listen to the whir of the engines the next time that you fly, and I encourage you to make note of how long it takes for the aircraft to get airborne. My experience has been from the low 30 seconds up to the low 40 seconds for liftoff to occur. Depends, of course, on how many passengers and how much luggage and how big the engines are. So if you want more videos like this, example problems, short lectures, physics.gpclements.com. If you're interested in introductory astronomy and some general interest things about astronomy, astronomy.gpclements.com. These websites are free, no registration. You'll find a list of the the videos, how long they are, a brief description, and a direct link to the YouTube location. And ask your instructor if you have questions.